up, guys? It's Jonathan Putnam. Today we're going to be learning about translocation into the mitochondrial matrix. Now for this video, can we get 10,000 likes, please? I know it's a lot, but I think we can do it. You know, if you haven't already, please hit that subscribe button. Also hit that little notification though, so that way whenever I post a video, you can get a notification. So, you know, I think we're about to start this educational video right now. Okay, so when considering translocation into the mitochondrial matrix, you have to consider there are a few differences between translocation into the endoplasmic reticulum. For sake of ease, let's consider a cytoplasmic ribosome as translating the protein. So we have the ribosome right here. And then the protein coming in and then reaching its tertiary or quaternary state after translation. However, we can't have that because when we are translating into the mitochondrial matrix, we're using post-translational translocation. So we need to have proteins from the HSP70 family or chaperonins come in and use ATP to keep this protein unfolded. So let me just draw a few of those there. Something like that. And have them come here. And so essentially the protein will be kept in a straight conformation, which is needed to get through the small channels present in the translocon. So it looks a little bit something like that with the proteins coming in and undergoing ATP to ADP, undergoing, you know, that energy transfer in order to keep it unfolded. So when we're in consideration of the mitochondrial matrix, the first thing to consider is that the outer protein complex is referred to as a Tom complex, and the inner protein complex is referred to as the TIM23 complex. And when we're translocating over this, they actually will pretty much jump over both membranes at the same time. So the protein will actually take on a straight trajectory. Let me erase that the best I can. You draw what I lost. Alright, so when we get close to here, actually, there are many proteins that will assist the translocation through the first membrane. Kind of like right here. And when we get through this first translocon, it's also worth mentioning that the signal reception particle and the signal sequence, the signal sequence is also working during this the post-translational translocation in order to remove the plug. So that's also present on this protein chain. But once we get into this intermembrane space, into the stroma, it undergoes the Brownian pulling model, actually, where bit protein will bind to the protein going through, being translocated. We'll have a look like that. And it also undergoes energy transfer, transforming the ADP into ATP. And in the Brownian pulling model, that energy transfer of binding and keeping the protein, you know, not turning into its tertiary conformation is enough to actually pull it through. So it differs from the Brownian ratchet model in that the binding of the ATP, that the binding of the bit protein only holds it in place, and it actually uses diffusion to go through. And during translocation to the mitochondrial matrix, as I said earlier, this essentially happens twice with bit protein. Here, I'll draw that there. Doing the same thing, undergoing energy transfer to pull it all the way into the mitochondrial matrix. Now, once it's in the mitochondrial matrix, it differs from either going into the cytoplasm in that it will be used up in a fairly short amount of time, seconds at least and minutes at most. That differs from the rest of the cell. Another thing worth mentioning is that the machinery used here is more similar to what the cell is using as opposed to what a prokaryote would use. I mentioned that because of the endosymbiotic origin of the mitochondria, using sec-A as a way to translocate. But this is the machinery used here is more similar to the parent cells. So, okay, I hope that was helpful, and that is how proteins are translocated into the mitochondrial matrix. Thank you very much.